Okay, let's go. This is collision theory, and we're going to be talking about kinetics. So this is really in the rougher part of AP chemistry, but we're going to get through this. Just make sure you listen to the whole video and take notes if you need to. Rewind if you need to. Stop, pause, whatever you need to do to get this material. So let's get started. So, collision theory. Collision theory. Definition is a theory that explains how chemical reactions happen and what affects the speed of the reactions. So example is, if you put more reactants together, you'll raise the temperature, or if you add a catalyst, the reaction will generally happen faster. Here we have the picture we have on the left. With a low concentration, there's fewer collisions because there's not that many things to bump into each other. We have a high concentration, we have more collisions, so the reaction is going to happen at a much greater rate because there's going to be many more opportunities for collisions. All right, kinetics. Kinetics is the study of reaction rates. Examples. So the nature of reactants, like what kind of things, is it acid, is it a salt? You'll learn about these later. Is the concentration, temperature, if there's catalyst present, pressure, physical state, they all affect the reaction rates. So whether something's solid and gas and reacting, all these things affect how fast a reaction goes. So here we have a reaction without a catalyst. We recognize this from before. The activation energy is really high, and the reaction with the catalyst, the activation energy isn't that high for that reaction, so it has a faster rate. Catalysts. So a catalyst provides an alternative route for the reaction with a lower activation energy. So we told you before that the catalyst lowers the activation energy. We lied. So it lowers the activation energy in a special way that we're going to explain more in depth now. Now imagine 100 people trying to climb a mountain. Now, only the people with the most energy are going to be able to climb that mountain, so it's not going to be that many people. So say we use a drill and we make a tunnel through the bottom of the mountain. That makes it an alternative route that requires less energy. So we didn't lower the mountain, we just opened up a easier way for people to get from one side to the other. So that's what a catalyst does. It just makes an easier route for the reaction to happen. So examples are iron in the reaction that makes ammonia, that's called the Haber process, and manganese dioxide and the decomposition of hydrogen peroxide. Remember, catalysts are not used up in the reaction. So they're there, they just help things happen. Intermediates. So it's a molecule or ion formed during a reaction that reacts again to form the actual product. So an example of this would be, okay, you have your cake ingredients, you have your eggs just out of the carton, you've got your sugar, your flour, it's still in the bag. Now, before those turn into cake, before those reactants finally turn into the final product, in the middle they're cake batter. So it's not quite cake yet, and the reaction's already started. But a reaction intermediate is what's in the middle. That's not the product, but it's still one of the steps that falls in the way. So here with reaction rates, we're going to see how we go from, we have the cake ingredients. First we open it up, we mix them up here in the first reaction, then we start heating it up here in the second reaction, and then we get our cake. So we didn't just heat up the flour and the sugar and the eggs and get cake. We had some steps in the middle, and we do the same thing with chemical reactions. Rate law. So, rate law is an equation that shows how concentration or pressure affect the reaction rate, and it must be determined experimentally in the lab. So you can't just think these things up. We have to actually get some data, find out how fast reactions go, and use that to determine the reaction rate. And here we have, this looks familiar from last time, we have the coefficients that were the subscripts, but M and N right here are only equal A and B for one-step simple reactions. So we're going to talk more about those later. Rate constant. So the rate constant K that was in that rate law, it helps show how fast a reaction happens. So if everything stays the same in this reaction down here, the bigger K is, that means the reaction went a lot faster. So if K is 1,000,000, then that means it goes really fast. If it's 0.00001, that means it goes really slow. Reaction order. Reaction order. So it's determined by the exponent in a rate law. It can be found for individual reactants or the overall reaction. So let's take a look. So we have the rate K times the concentration of A, and it's only raised to the first. We don't usually write the 1, but in this case I wrote it just to show it. So we'll say that this reaction is first order because the exponent is 1. Let's look at this other one. This reaction isn't first order, but it's first order with respect to B. So you can either say first order with just one part of it, or you can just say first order overall. So with respect to B, this is first order, and overall, this is a first order reaction. All right, first, second, and third order reactions. So this gets a little more complicated, but the same idea. So we're going to see the sum of the exponents. So let's check it out. So we're going to add all the exponents in this rate law, and we get 1. There's nothing else. So it's first order overall. Let's take a look at this one. So here there's 1s here, but we didn't write them, and there's a 0 for carbon. So it's first order with respect to both nitrogen and hydrogen, but overall this is a second order reaction. That's because 1 plus 1 plus 0 is 2. So we got a second order reaction. So we're going to add all the exponents and we get the order of the reaction. Zero order reactions. Now this is something a little bit different. So say the sum of the exponents is 0. That means that the concentration or the pressure have no effect on the rate of the reaction. So we'll write that as like this. So the rate equals K. So because something raised to the 0 is 1. 10 raised to the 0 power is 1. 500 raised to the 0 power is 1. So here we have, again, it's first order with respect to nitrogen and hydrogen, and 0 order with respect to carbon. It's still second order overall, but we can say that it's 0 order. The concentration of carbon has no effect on how fast this reaction goes. All right, so I hope you paid attention. Hope you took some good notes. Watch it again if you want to. Tell your friends, and now take that quiz.